Hello, my name is Michal Kuritka, and today I will talk about KGB. I'm a platform engineer in EPSA Group, and our project called KGB is an open source CNCF sandbox project, and KGB is a DNS-based global load balancer running on the distributed Kubernetes cluster. It supports several load balancing strategies. In IT and other technical disciplines, we need to balance some variable. For instance, in the world of photovoltaics, you want to route the energy between particle batteries. Maybe you don't want to route the energy. Maybe you want to optimize your cycles on the batteries. On the other hand, in the IT, you usually want to route traffic between particular nodes. Under node, you can imagine, for instance, VM, pod, it could be cluster, it could be region, it could be application. Very famous load balancing strategy is failover. In failover, load balancer routes traffic into the one primary node. The primary node is synced into the secondary node, and once you lose the primary one, load balancer detects that it starts to route traffic into the secondary one. This is very useful for high availability scenarios. If you require performance, maybe the round robin is the right option. In the round robin, the load balancer routes the traffic into particular nodes equally. But what happens if one of the node is much stronger than the others in terms of more CPUs, in terms of it having more memory or better connectivity? In such cases, you can choose the weighted round robin. In weighted round robin, you set how the node is preferred to the other. Now imagine you have like a few nodes, one with very large weight, for instance 9, and the second one with weight 1. So the first one is like 9 times stronger than the second. You deploy the web application like an eShop and start to use that. So you connect to the eShop, see the login page, start to do some shopping, and finally you want to click on the button purchase, and bam, everything is gone. You are back on the login page. It is because you lose connectivity to the first node, and load balancer routes you to the different one, and you lose the session. And nodes are not synced. So maybe in such case, you can use consistent hashing. In consistent hashing, the load balancer can read session ID or some identifier within the session, and based on that identifier, it attaches concrete node. So if session has identifier XY, it goes to the left node. If it has like a ABC identifiers, it goes to the right node. The consistent hashing has almost one advantage. It is when you add or drop node, it will affect as minimum sessions as possible. And now maybe you don't need to route the traffic itself. Maybe you can let load balancer just return of target, and the traffic goes directly to that target. Like in the DNS, you just retrieve the IP address, and all communication, all the traffic goes directly from the client to the node. We use the DNS load balancing for that, and it could have also the disadvantages because the retrieve records contains TTL. There is the possibility that if you lose node, all traffic is still routed into the died node until the DNS resolver refresh the cache. So for very highly performance scenarios, the DNS load balancing doesn't work. But for the most of the scenarios where you can be some like a couple of seconds or minutes be off, the DNS load balancer is great, powerful tool. Now imagine, once I had a task to implement the high available infrastructure. I wrote my terraforms. I had two regions with the database replication and had the infrastructure there. And in front of those two regions, I had one single load balancer. So the question was, what happens if I lose that load balancer? Of course, I will lose connectivity. So it means the whole infrastructure will be unavailable. So it wasn't like a highly available, but it has a solution. You can install load balancer for each node. Then any load balancer will be able to route traffic to any underlying node. And if you lose node, the load balancers will be able to route traffic to remaining nodes. So what solution we usually need? We want it must be running in Kubernetes cluster. No single point of failure. It must be open source, and it must support several load balancing strategies. And that's where KGB is coming. KGB itself, how it is work, it's quite difficult. And you can visit our web pages, kgb.io, where you can find how KGB is exactly working, step by step. But very briefly, KGB is an operator running within the Kubernetes clusters. It knows the GSLB CRD, and GSLB itself contains the configuration of the load balancer. And once GSLB is installed into the application interface, the application becomes to be load balanceable. In this example, we have application with host demo cloud example.com, and it is running on both clusters, and it is load balanceable with the configuration within the GSLB. You don't need necessarily to create the GSLB resource itself. You can only update or extend ingress annotation, and the KGB operator will create the GSLB for you. And when it is created, the application is load balanceable. It knows somehow, via some kind of sync, it knows the IPs of the all load balanceable applications across the all clusters. So if everything is healthy, our internal core DNS services through the zone delegation will retrieve you the IPs of those applications. And if any of those applications is unhealthy, the KGB detects that, and the core DNS instances, KGB core DNS instances will retrieve only the IPs of the healthy applications. So we fulfill all points. It is running in the Kubernetes clusters. There is no single point of failure, thanks to the zone delegation process. It is open source, and it supports several load balancing strategies. Demo time. In demo, we usually present failover strategy by changing the ingress annotation right here. But now I will present the wait round robin using the GSLB itself. If we inspect the GSLB configuration, it contains the strategy field having a round robin with the weights 1 for the European cluster and 3 for the US cluster. So let's do the demo. For the demo purposes, I will use the makefile, and makefile contains only standard kubectl commands and the Helm. Nothing special here. Let's inspect the clusters. I'm connecting to the, I have two clusters, the GSLB1, which is the European one, and the test GSLB2, which is the US one. At the moment, I'm connected to the US cluster. If I see the pods, I can see only KGB namespace, which necessary KGB pods, nothing else. Cluster is more or less empty. I want to create application which will be load balanceable. So I will create namespace demo on the two clusters. Deploy namespaces. I'm running standard kubectl commands for creating namespaces on the both clusters. Installing application there. Make deploy app. Application is podinfo. I created it with a Helm. If you don't know podinfo is simple web application used by many CNCF projects, used for the end-to-end testing. Let's see how the application is working. Podinfo U and run for US. So I'm running two instances, one of the view cluster, you can see, and the second one on the US cluster with a different color. Okay, so applications are running thanks to port forwarding. So now we have some initial state. There is nothing special here. I want to make application load balanceable, so I will install the GSLB. Make deploy GSLBs. This command installs the GSLB on the both clusters. Because GSLB is created, KGB operator automatically created the ingress for the application, checking the health, etc. Let's inspect the cluster. So from that, podinfo is ready. GSLB. GSLB on the US cluster is also ready. Ingress. Okay, there is ingress and it has some IP addresses attached. In the next step, I will do the testing. This is my laptop, and I will connect to core DNS within the KGB. And this core DNS will retrieve me the IP addresses from the both clusters, from the European one as well as from the US one. But the US, because we set weights, and it is weight round robin, the US will be preferred to the EU cluster. So let's inspect log on this core DNS instance and run the big command. And you can see here that the US is preferred to the EU. So the US IP addresses are on the top of the list. You can see it here. Run the dig command again. Okay, if I run it, the US should prefer to Europe. Okay, so what if I write the output log to the file log.log and run the dig 500 times. Let's wait a couple of seconds until the command will finish. Okay, done. Let's see the log file. And here in log file, we have the particle outputs. So let's check how many the US. We have 372 results for the US. And the EU. So EU with a different weight. We have 144. So as you can see, the US is quite 3 times more preferable than the EU preferred resources. So everything works as expected. From the demo, I want to remember you 2 things. First of all, the GSLB is the resource which makes application balanceable. It contains some configuration of the load balancer. Second thing I want you to remember is that you don't need necessarily GSLB. You only need to update ingress annotation, and PGB operator will create the GSLB resource for you, which makes application load balanceable as well. I hope you enjoyed the demo, and thank you very much. Please start our project and drop any question in the Slack or GitHub or whatever. And if you like, you can join our team. We are still hiring. Thank you.